Eu abro meu laptop e a gente transmite aqui. Ok, vamos começar então. Tem certeza que tu abriu a transmissão?
Todo mundo adicionado na palestra. Adicionado a transmissão.
Ok, tá.
Tá, todo mundo ali.
Bom, então eu sou o professor Wagner Anabor, como parte do ciclo de palestras do Programa de Pós-Graduação em Meteorologia, nós convidamos hoje o Dr. Ricardo Reinoso-Rondinel, que tem sua área de concentração em pesquisa na área de meteorologia por radar, vasta experiência no campo de aplicações de radares de última geração, trabalhou como pesquisador e estudou no National Severe Storm, National Weather Center nos Estados Unidos, concluiu seus estudos em radar também na Universidade de Delft, e sua área de concentração principalmente radares de banda XK, e hoje ele vai nos falar um pouco sobre as aplicações deste tipo de equipamento. Essa palestra é de extremo interesse para a Universidade Federal de Santa Maria e o Programa de Pós-Graduação em Meteorologia, pois vai permitir à comunidade acadêmica compreender melhor as aplicações desse instrumento. Nós estamos recebendo um radar de banda KX aqui e vai abrir muitas possibilidades de pesquisa. Então, seja bem-vindo, Ricardo. Ricardo, I would like to thank you for being here and you give you the space to start your presentation, or if you need to say something. Welcome and have a nice talk.
Okay, thank you, Wagner, for the introduction. I'm happy to be here and to share a little bit of my experience and to let you know some capabilities of radars for meteorology research. The applications of X and Ka band radars for meteorology. So today I'm gonna go through the following points. I will start with some motivations on monitoring of meteorological systems using weather radars. We'll focus on the X-band radar with dual polarization. Later we'll go to the dual frequency and a little bit of the processing that is needed to work with radar data. So I'm going to start with some motivation. Maybe I don't really need you to convince why we need observation from radars, but it's an important topic because it's very important for us, for meteorological service and research, to monitor and to give warnings about severe storms, as well as to improve the models that we could use from the observations. Let's start with maybe some typical examples of radars. One typical example of radars is to monitor and provide measurements of precipitation. So here in the left panel, you could see an animation of how the rainfall rate evolved with time using multiple radars here in Germany, for example. Another application that you could use to study severe weather is to do some identification and tracking of storm cells. It's a very typical topic as well that is mostly well known in the States, for example, of severe weather. And another one is, for example, to use observation from weather radars to validate numerical weather models. So, for example, here you see precipitation provided by models forecasted ahead on time, and here you see the observations. So maybe that's where this talk will go towards that direction. That is important for us to a way to study better and to identify better microphysical processes that happen in the whole evolution and the structure of the cloud, going from a few kilometers high all the way to the surface. So all these processes that happens in the lower troposphere is it's very difficult to monitor, and maybe that's why the motivation comes to bring multiple radar systems at different frequencies to study cloud properties and also precipitation properties. Here in the bottom part, you see some typical wavelengths of radar systems that are used to specifically study this kind of systems. So let's start with why we need X-band radars. Normally, the observations or monitoring of weather is done by larger systems working at a different frequency or different bands. And the problem with those typical weather radars is that they miss very often observations at low altitudes, so near the surface, because those radars are of high range or light range detection. However, X-band radars are more or less smaller radars, and they could be one solution to avoid the gap that is often happen with conventional radars at S-band or C-band frequencies. So the idea is that maybe in some countries people could install small radars, cheaper radars like X-band radars, in order to minimize the gap. So here in the lower panel, you see on the left panel some retrievals of rain-for-rain maps, and then you see in the right panel how using measurements from X-band radar, which is more or less indicated with this circle. So that's the range of the X-band radars called JUXPO. And then you see that using this X-band radar, you could improve the estimation of rainfall rate that reaches the ground, because this radar is smaller, but it's able to minimize the vertical gap that is often happen with conventional operational radars. Another application of X-band radars, again, because it's a smaller system, normally conventional radars have a 1 kilometer resolution, but the X-band radars goes down to a few hundred meters, so sometimes 100 meters, sometimes 200 meters, or more or less in that range. And they give you a better description of the system in terms of the spatial distribution of the radar echoes. The problem with X-band radars is that they will suffer from attenuation. So the location of the radar is here at this point, and because of rain, what the echoes that happen behind the precipitation system sometimes are not observed very well by X-band radars because of the severe, well, not severe, but strong attenuation processes that happens in the propagation, right, of the waves. That's more or less the main disadvantage of small X-band radars. One thing that I wanted to discuss, or to maybe, I don't know if you know, but I want to introduce what is a resolution volume. Resolution volume is, let's say, a box in which there are multiple particle hydrometers, which contributes to the radar, to the echo, back to the radar. So when we measure, when I show you these maps, there actually are an average value of multiple particles that are enclosed in one box, and that box is called a resolution volume. That's where you see some pixelized structure in the map. But that's how it is. This is how the radars works. So just to keep that in mind during the rest of the presentation. So then we move to the precipitation part of this talk. Just one more thing to clarify: the raindrops are not like these tearing drops. This is not correct. A better representation of the size of raindrops is more or less what we are picturing here on the right-hand side. For a small size of raindrops, they are typically spherical. But as the raindrop increases in size, the shape also changes, and it tends to become more oblate, a bit more wider in the x-axis than in the y-axis. And this is something important. This more or less motivate the notion of dual polarization radars. So normally a radar will just only use one polarization. So it will just send a one, let's say, horizontal pulse, and it will give us information about the size in the x-axis. But this will lead to errors in the quantification and identification of different particles. So a better way to scan or to estimate the sizes of the particles is by sending a cross polarization wave. So a cross polarization, so a vertical polarization wave, in which it tell us a bit more about the size in the vertical axis as well. So then we could have a ratio of power in the horizontal and in the vertical axis. This polarization technology is not new. There has been a lot of research in this topic. However, remains still very challenging to really bring research into operational activities. So there is still a lot of research going on in dual polarization. How can we really use the information, because we need to process the data, and we still need to do more research on the field of polarimetric radars at different wavelengths. Normally, when you have a radar system, mostly people use reflectivity, which is the Z, or reflectivity factor. But because of polarization, then we could have a few more variables. And there I list typical polarimetric variables from radar. We have reflectivity. We also have differential reflectivity. I will explain in a little bit what is differential reflectivity. We also have differential propagation phase, and we have a specific differential phase, which is the range derivative of the differential phase. And a copolar correlation coefficient, I will not explain in detail, but this is more or less a measurement of how the power in the x-axis and in the y-axis are similar to one another. So let's start with the differential reflectivity. So here in this equation is very simple. The is different between the echoes in the horizontal and in the vertical axis. So, and it tells us a bit about the shape of the particle, right? So if the particle has this oblate position, of oblate shape, then the differential reflectivity, or ZDR, will be a positive number, larger than 0 in dB units. So as an example here, you could see on the left panel the power. So this is reflectivity, and you see a very strong frontal precipitation system. The radar is here in the middle, where I'm pointing. And then, but I don't know how big they are, I don't know what the shape of the drops, right? But if I show you the map of differential reflectivity, then you see areas in which we have probably small drops, which tends to be spherical. And this is the blue area in which the difference is near 0, because the power in the x-axis is similar to the power in the y-axis. But when we observe the leading edge of the squall line system, then you see areas in which this difference is larger, as near as 3 or 4 dBs. And this allows us to identify in which areas of the system we have bigger drops, medium drops, or spherical drops. So this is more or less an example of how we could use this ZDR. Pay attention also to these noisy areas below the radar, and that's because there's no significant echoes, or there's no precipitation echoes, and those often they need to be removed from the map. So this is what happens for liquid drops, for droplets. But we can also have observations of ZDR for ice. And the ice, typical ZDR echoes tend to be smaller than the water because of the electric properties of ice. And then here are at least some examples of ZDR values or range values for different particles like hail, gravel, or snow. Here you see some images of how those hydrometers look like. So this is a bit more, it has more variability on the shape, and it's more difficult as well for us to identify which one is which one and to also measure. So that's why it's still quite challenging to really have a very accurate values of those polarimetric variables. However, we have many more, and that also helps to have a better retrieval of those hydrometers. So let's move now from the power variable to the phase variable. So as we send two waves, one in the horizontal and one in the vertical, the horizontal will try to slow down because of the drops in the propagation, right? So if we have only spherical drops, the horizontal and the vertical waves will travel at the same speed, but because we have, let's say, objects which has more or less big raindrops, then one will go faster than the other one. So one will come back faster to the radar than the other wave. And that phase is called the differential phase. Another way to explain, for example, if the radar is at the origin of this at this point, and then we have a range system here. So what will happen that this difference will increase with range, right? That's nice, that's good to have, but we cannot really tell in which area is the range. So what we usually do is to obtain the derivative of this increasing curve. And derivative is what we call the specific differential phase, or KDP. So this is what we always do. We're trying to find the derivative in range. Here in this right-hand side, we see an example in which we have, let's say, 1, 2, 3 storm areas, or 3 regions of precipitation. And then we see that the differential phase goes from 0 degrees to 20, then after increases to 70, and then goes to 80 degrees. In order to know by how much the differential phase is increasing, we do again the derivative, and then we have the KDP values of, for example, this region by 2, increases by 5, or increases by 1. And these values tell us a little bit about how many drops are in this area, how many drops and how spherical they are, or how oblate, how bigger they are. So it tells us a bit more than reflectivity, right? Reflectivity only tells us that if it's bigger, then we have bigger echoes, stronger echoes. But KDP, it tells also the size, but also it tells how many they are, how many of those drops are concentrated, because then the differential phase will be bigger too, right? So this is another variable interesting on KDP. One thing before I go to the next slide is that this differential phase is independent of attenuation. So before I say the X-band radars are sensitive to power attenuation, but the phase is independent of attenuation because it just tells us how quickly one comes back to the radar and how slow the other one is coming back to the radar. So, but there is attenuation, but we don't care because the differential phase is just the phase of the signal, not the amplitude of the signal. So now I can go to the next slide. Here's an example of this differential phase. So now the radar is scanning 360 degrees, and we have a map of this differential phase. Again, at the beginning, close to the radar, near the radar, we have values of 0, and we move away from the radar, then we have increasing values of 70 degrees, for example. And below here is the derivative of this differential phase. Why is it so important that we want to have KDP? So why we want to have KDP? Because here in this simulation, we have a near linear relation 1-to-1 between KDP and rainfall rate. Radars don't measure rainfall rate, but we could obtain KDP, which tells us we could infer from KDP rainfall rate. And this is here below the theoretical curve or relation between reflectivity and rainfall rate. When you see that reflectivity is not very easy variable to estimate rainfall rate, and it is not a non-linear behavior between these two variables. So I talk about the horizontal scanning monitoring, but what about a vertical scanning monitoring? So this is what we call the range height indicator. Here we see that the radar could also go up in the vertical, and we could have a map of what's happening in the cloud from 0 to 10 kilometers, for example. Here in the differential reflectivity, you see a very clear line of the melting layer, so ice particles, which is giving us a bit of high differential phase, and because they're tend to be oblate as well. And here you have probably big drops as well of strong echoes of differential phase. So with this, you could obtain again, you could sample the storm. This is an RHI X-band frequency as well as an example. You could see some dynamics happening in the storm, some updraft and downdraft. You could see KDP columns, which is also a very hot topic for microphysical studies, which tell us about the liquid water content of the storm. And then with combining those multiple polarimetric variables, what you could do is to classify the type of hydrometers, and that's what we call the hydrometer classification algorithm. And then you could have a different a categorization of those particles that happen in the vertical axis and in the vertical distribution and in the horizontal distribution. And you could monitor this to study the evolution of convective systems, right? But well, normally radars don't do this kind of scanning. This is mostly for research only. One way to use the volumetric scanning, so the radars will do this volumetric scanning every 5 minutes. One way to study microphysics is by estimating a quasi-vertical profile. What is a quasi-vertical profile? Well, let's say we use only the scanning at 20 degrees, and then we average in azimuth and in range, and then we have more or less a representation of the observations of those polarimetric variables, what I explained before, reflectivity, ZDR, KDP, and then we could show this evolution with time. So this is a way to see the evolution of the precipitation system, going from 0 kilometers, for example, in this illustration, up to 8 kilometers. Then you see how the precipitation evolves with time. So you map in here reflectivity, you could have the differential reflectivity, you see again very clear precipitation in the lower areas, you could have a detection of the melting layer at this height of 1.5 kilometers high, as well as other microphysical hydrometers are created in high altitudes. KDP as well, you could have a very nice map of KDP by doing this, by estimating these QVPs. So again, the radar will do this volumetric scanning normally, and from there you just averaging the polarimetric variables to have a time evolution of the system that you could allow us to study more or less the evolution of the vertical and horizontal structure of the system, right? This is important too because it helps us to reduce the noise. There's a lot of noise happening as this is an instrument, right? So we have always noise, and one way to reduce the noise is by averaging. And this is a cool way, I think, to do using these QVPs, or quasi-vertical profiles. This is relatively new way to visualize the evolution of the storm. So now if we move a little bit now to dual frequency. So in some places, not everywhere, this is very difficult to do, but in some places you have multiple radars working at different frequencies, at different wavelengths. So I brought here a summary of some research done by the ARM, which is the atmospheric radiation measurement. Probably you heard about it. And in Oklahoma, for example, they have multiple radar systems at different wavelengths, for example, C band, X band, and also a combination of Ka band and W. So those are cloud radars pointing mostly vertically. And you have collocated or nearby radar system at X band, for example, here, which are called precipitation systems. So they measure weather, precipitation, and the cloud radars, well, on the KA and the W radars, they measure clouds droplets, right? So this is more or less an example in Alaska as well, in which they have something similar to what you will guys have sometime, I think soon. It's a combination of a KA band system with an X-band radar system, which allow us to study more or less the vertical, not only from small drops of clouds, but also for precipitation, right? So those more or less is a combo of multiple frequencies, which are very cool to have, because they allow us to study more or less the whole structure of the precipitation event. Something cool that these systems allow us is to identify super cool liquid in mixed clouds. So you have ice, but you also have water. You could retrieve air motions, and you could also detect the drizzle, so the very small particles before it becomes proper rain. It also allows not only to identify, but to quantify moments from the distribution of hydrometers. So we could have mass, we could estimate size, number of concentrations, so how concentrated they are in specific at different heights. We could have water content, and therefore also rain rate with the X-band radar. And this helps us to reduce the uncertainties. As I said before, in ice is very noisy, so it works better when we have two frequencies working. And not only two frequencies, but also with dual polarization. And on top of that, with Doppler information. And Doppler information is also very rich. It tells us, I will show you a bit more about why Doppler is also a very important capability of radars for studying microphysics. So let's go to the next slide. Here's an example of, for example, here on the panel A, you see a KA band radar pointing vertically, and you see here, for example, low echoes or low reflectivity values, and here you see a very strong reflectivity values. Here you see the, again, profiles of the KA band radar, which tells you more or less the turbulence of the system. So this is called spectrum width. And we also have a micropulse LiDAR, which tells us about the depolarization. So as I said before, the depolarization is how similar or how different, or how asymmetric are the particles, right? But this LiDAR was there because back in the time, this KA band radar from the ARM, it was single polarization. And now they have a dual polarization, they upgraded it. But in this study, they have to use this LiDAR in order to tell us more about the shape of the particles. What can we do with these profiles? So if we focus, for example, in the first hour, so in the interval from 4 to 8 UTC, we want to identify what kind of hydrometer it is. So for this group, from A4 to 8 UTC, what we see is we have a low echoes of radar reflectivity, as you see here, and you see also a low linear depolarization ratio, which is typically a signature for spherical drops. And that tells us that at this time, at this altitude, we have probably super cool liquid water. Now, if we move to segment B, from between 14 and 18 UTC, we have high echoes of radar reflectivity and relatively low linear depolarization ratio, which is also typical for small spherical particles. And that tells us that it's probably a mixed phase, because we have low linear depolarization ratio, but with high echoes of reflectivity. And then also in the high top here, more or less, we have a mixed phase condition, because we have a spectrum width which is a bit wider. When the spectrum width is wider, that means that there is more than one species, so more than one hydrometer class. That's what we could infer, that it's not just liquid, it's also not just ice, but it's a mix of both. So the message here is that with this profiling and with let's say dual frequency, let's call it this way, or with polarization, polarization information, you could retrieve, you could pinpoint which kind of hydrometers are at which time and at which altitude. Another example is when we have a combination of two frequencies. So here we have the KA radar with the W, so both are cloud radars. And we have here a vertical pointing KA radar. So when let's focus now that we have a vertical pointing, and because this is a Doppler radar, we could have Doppler information. So here in the x-axis, we have the velocity, and the y-axis, we have the altitude, the height. And then you see, for example, echoes that happen, for negative velocities, what it means is that particles are falling to the surface, and near zero velocity, it means that droplets that are suspended, right? Or positive if they're going upwards. So if we focus on the left side of the spectrum, we have very high echoes of Doppler contributions, which maybe tell us about that there is a higher density of ice particles, around 1 kilometer. But if you move a bit more higher, then probably you have less dense groups of ice particles, because they fall, but they fall less faster than those ones here, right? So more or less, this is the vertical distribution of those ice particles. And then if we now combine this dual frequency, so now let's say, as I explained before, we have these quasi-vertical profiles. So we have 20 degrees elevation, and the radar will do this canonical scanning. And we focus only at this height of this angle of 20 degrees. We could obtain profiles of different polarimetric variables. So for example, here in panel C, you have in red, you have the reflectivity. That is more similar to this spectrum, because you have a low altitude, you have more values or higher values of reflectivity. And when you increase with high, the echoes or the power tends to decrease. And the black line, you have the ratio between the reflectivity at Ka band and at Wa band. That's also something good, because it tells us about the size of the particles. So DWR is the differential wavelength ratio between these two radar systems. In your case, you will have a Ka and A X-band radar, but in this case, it's the KAW radar. And here on this panel C, we have, again, a vertical profile, or a cut, of KDP, and which has KDP in black, and the differential reflectivity in red. These two variables tell us about the ice water content, as well as the size of the aspect ratio of the particles. So because this is in Alaska, so we're talking about ice particles most of the time. What can we do with this information of Doppler, ZDR, reflectivity, and two dual frequency? Well, the idea is that doing some analysis of these profiles, we could map more or less the spatial variability of microphysical of hydrometer particles and microphysical processes. So, for example, here we have maybe less dense particles, which could be a signature of aggregation of ice particles that happens more or less at 4 kilometers high, and at the lower high, between 1 or 2 kilometers, what we could see here, because of the signatures on the left, we could probably infer that we have a growing system dominated by rhyming. So this is more or less the advantages of having dual frequency, dual polarization systems for studying the particular structure of clouds and precipitation. Before I finish my talk, I wanted to also introduce a little bit of that there is also, we need to also consider the data, the processing of the radar data, because we need to remove non-hydrometer particles, non-hydrometers echoes. We need to correct for power attenuation. We need to estimate also dual polarization variables. Of course, sometimes the radar system comes with those variables, but we could always do better, right? And obtain QBPs profiles, as I showed you before. So here's an example of KDP. When you have a better estimation of KDP, you can keep the spatial variability, and sometimes, depends on which algorithm you use, you could have a poor quality of KDP. here in the bottom plots, you have power, so radar reflectivity and differential reflectivity at X-band frequency. As I said before, they suffer from attenuation, power loss. And actually, this is the truth. This is after correction for attenuation. So it's very important you guys take care of your data. And the good news, actually, there is a lot of effort from the community on radars, from clouds and precipitation radars for processing this data. And this is an open community. There is a lot of free access to obtain not only data, but also to obtain codes and algorithms to process your data. For example, there is a lot of projects, and I will probably point the community of the ARM. So the ARM, they have similar radar systems that you guys will have soon. And so I think you guys will have a good advantage by looking or resourcing your codes at using these open source platforms. And that's it. So now we'll just summarize my talk with the advantages of X-band radars, which will give us a high resolution observation and monitoring precipitation close to the surface to reduce the gaps. Polarimetric information tell us a bit more about the identification of hydrometers and the quantification of hydrometer size distribution moments. Scanning Ka band radar here. It could be used to study the vertical distribution or spatial distribution of clouds, hydrometers in clouds. And probably the most strong point here is the combination of dual polarization, dual frequency with Doppler information, which I think could unleash the potential of observations to improve the understanding of the life cycles of clouds and precipitation system, as it will help us to improve our understanding of such as very challenging processes that happens up in the air, right? So I think with that, I finished my talk. Hopefully I give you some impression of what you can do with those systems and what is the benefits. Yeah, and if you have some questions, please let me know. We could always have some discussion afterwards. Thank you.
Thank you, Ricardo, for your presentation. I do have two questions. Thank you, Ricardo, for your presentation. I do have two questions. Thank you, Ricardo, for your presentation. My first question is, it's more general, like if you have some advice for students who wants to get engaged in radar meteorology, yes, and what would be important skills to develop research in this area?
Yeah, that's a good question. Yeah, I think having these radar systems really complement a lot of that theory or the theory needed to do models from the meteorological side. So what you need some skills is to get involved in some literature or courses on how to process, first to understand the observation from polarimetric radars, and then also to be familiar with the processing of this data to make good interpretations of the data, because that will tell us the information that we need to understand our research in meteorology and in cloud research and precipitation research. So there's a lot that one could do with the observations, but I think it's very important to have some knowledge on theory on radar meteorology. I don't know if that more or less answers your question.
And the second question is more related to your presentation. I would like to understand your opinion about X radars. As I understood, S-band radars, which were a way more popular in severe weather monitoring around the world, they are less versatile as a research tool for atmospheric circulations, cloud microphysics, and even for severe weather applications. I don't know if I'm correct. Would like to do a comment about that.
Yeah, X-band radars. They have the capability of giving you finer resolution or high resolution observations, but mostly of severe weather. But also it has a limitation, as I said before, is the attenuation. So when you have a very convective system, one X-band radar will be limited. Sometimes what people do is to have a network of X-band radars, so then you could more or less complete the map or the image of the system, right? But it has more sensitivity as well to small drops. So you could have more information about, no for bigger drops, but also for small drops. And it's getting popular, these X-band radars. They're cheaper than the conventional operational bigger radars. But I think a lot of people are having advantages or benefit from using a small X-band radar system with polarimetric capabilities. Without polarimetric capabilities, an X-band radar won't be of usefulness so much. It won't help you too much. It has to bring polarimetric capabilities.
Now we're going to open to the community if they have some questions. Não sei se vocês tiverem alguma pergunta, vocês podem perguntar em português mesmo, ou espanhol. Ou... Murilo? Não. Okay, so I would like to thank you, Ricardo, for your time and your presentation. For sure, it's very important to our students. This presentation is going to our YouTube library, and we'll be there for consulting in the future for other students in the Brazilian meteorological community. And we are looking for the opportunity to cooperate, since we're going to have a X-band radar here, and maybe for a presential training, we're going to schedule something in the future to have you here and get close in this research area. Thank you.
That you guys are getting this system. Thank you very much. Thank you very much again for the opportunity.
Okay, so thank you everyone. We are finishing this transmission. Thank you for watching, and you could send questions right to me, or maybe directly to Ricardo. We're going to be happy and share information in the future, and mainly related to this area of X-band radars and K-band radars application. See you next time. Thank you.
Bye.
Okay.